So in this video, we're going to take a look at how to determine what type of forces a certain molecule or substance will have in a sample of it. So to do that, we're going to use this chart over here. We simply ask these questions as we study the substance that we're dealing with, and then follow follow the path until we get to our answer. And so we're going to do a bunch of examples in this chart over here. We're going to take a substance and determine what type of forces that exist within it. You'll notice most of these forces are intermolecular force, and then we also have intermolecular forces, so dipole-dipole, hydrogen bond, London dispersion, and then we also have the ionic force found in ionic substances. So these are the intermolecular ones here, and this we still define as a intramolecular force. But it does keep various parts of crystals together. So when you have an ionic compound, your intermolecular force and intramolecular force are essentially ionic forces. So let's go ahead and try some examples out. And we'll use the flow chart to try to figure out what type of forces we have within the various molecules there. So we'll start off with water. So what I do first is I draw out the molecule. So we have H2O. I'm going to make a Lewis structure for water. And then with Vesper, you would know it was bent. And what I'm going to do is I'm going to go to my chart and see the questions that are there. So first of all, one of the questions is, are there ions present? That basically means, is it ionic or molecular? So if it's ionic, you'd say there are ions present. If it's not, you'd say no. So we don't have any ions present, so we're going in that direction there. Are the molecules polar or nonpolar, essentially? So are there polar molecules present? So is water polar or nonpolar? So let's go take a look at that. So I asked myself a couple questions. First of all, are there polar bonds? And so if you find the electronegativity difference between hydrogen and oxygen, you would see that there are polar bonds. The electronegativity of hydrogen is, let's just go to the periodic table, 2.1, I believe. Yep. And the electronegativity of oxygen is 3.5. So 3.5 minus 2.1. And we get 1.4. So that means that bond is 1.4, yeah. That bond is polar. So we do have polar bonds. There's actually two polar bonds. And then, so that's good. So yes, we do. And then two, around the central atom, are there lone pairs? So are there lone pairs around the central atom? There are. There's two lone pairs. So because we have lone pairs around the central atom and we also have polar bonds, we can say that this molecule will not be symmetrical. The dipoles won't cancel out. In other words, it's polar. It's polar. And the more electronegative atom is oxygen, so the dipole will be in the direction of the oxygen, the partial negative charge there, and the partial positive charge will be where the hydrogens are. So this is the overall direction that I drew there. But long story short, this is a polar molecule, so yes. So our next question is, are there any HO groups, HN groups, or HF groups? So there are. You'll notice there's an OH group. So yes, there is an OH group. And so what that means is that we have hydrogen bonding possibilities. So this molecule is polar, and it has therefore hydrogen bonding. That's what water does. So we can say that it is dipole-dipole, but in reality, the dipole-dipole present there is actually hydrogen bonding because of the OH group. I'm just going to put that there, OH group. And the other thing that water also has, just like every other substance, is the London dispersion. That's the default. But the strongest force in water is going to be the hydrogen bond. That's the strongest force in water. And so that there's how I would figure out the forces found within water. Let's try another example. Let's try the next one, CH4. So let's just erase this. And if you need to see this ink again, you can just rewind on the video there and then just see the example again. So we want to see if CH4 is what forces it has within it. So let me choose a different color here. Let's go with the green. CH4, which is just methane. First step is I'm going to draw a Lewis structure like this. And according to Vesper theory, when you have no lone pairs and only bonded atoms, 4 like this anyways. If you look at your VSEPR chart, you'd see this is tetrahedral. And if you want to draw a 3-dimensional image, just to show you, it would look like this here. And that's from the VSEPR chart in your data table. One coming out of this and one going behind. But we need to figure out if this is ionic or molecular. Now this is just non-metals, so there's no ions present. So it's a molecular compound, so we're going with no again. We're going in that direction to the left there. And we want to figure out if there's any polar molecules present. So we first of all need to check, one, are there polar bonds? So is the bond between C and H polar? Because it's all CH bonds, right? So the change in electronegativity is, I think, 2.5 minus 2.1, which is 0.4. So this is a non-polar bond. So we say there's no polar bonds. And then we also ask ourselves next, are there any lone pairs around the central atom? And there's no lone pairs. They're all bonded pairs. So lone pairs, no lone pairs. So because there's no lone pairs and because there's no polar bonds, overall this is a symmetrical molecule, so it's non-polar, meaning there's no partial charges there. And so our question is, are there polar molecules? No, there's no polar molecules. So really the only force that can exist when you have a non-polar molecule is the London dispersion force, the LDF, and that's pretty weak. That's why, for example, if you look at CH4 versus water, at room temperature, CH4 is a gas and water is a liquid. So when you have water at room temperature, the water particles are held together by their hydrogen bonds. So kind of like this over here. So another water here. That's partial negative here, like that. And this is the strong H bond, Whereas the CH4 particles, they're only held together by weak London dispersions. These can be broken pretty easily. Don't need much energy. That's why they're gas at room temperature. But the water is liquid at room temperature because you have to break the H bonds. They also have LDF you have to break, but really the strong force there is that H bond that you have to break to evaporate it. So that's why water is liquid at room temperature, but methane is a gas at room temperature. Let's do a few more examples together to make sure we really get the hang of this. So let's go ahead and try. Let's erase that there. Let's do the next example in our little example in our worksheet there. And it starts off difficult, but you get better and better at it as you practice more and more. So the next example is HF. Okay, so HF. Let's do a different color. Let's do that there. Here's HF. And if you did the electronegativity difference, you would see that it is an electronegative substance. And we'd have a partial negative charge here and a partial positive charge over here. Because they're two nonmetals, we're going to go with there's no ions that are present currently. We're assuming this is not the acid, but this is just a gas. I should have mentioned that. So this is linear, and because it's linear and we have a dipole, this is going to be polar overall, right? Because you have a pulling in a certain direction, it's not being balanced out by pulling in another direction. So linear with a dipole is going to be polar. So we don't have any ions. Are there polar molecules? Yes. In those polar molecules, are there any HO, HN, or HF? Well, yes, there are, because we have HF. And so if we have HF, that means we have a hydrogen bond that's happening. So between particles of HF, I'm not drawing everything out here, but, well, actually I will, why not? We have a hydrogen bond that occurs like this. This is the partial negative, this is the partial positive. And so this is a hydrogen bond. And that's because specifically there's an HF there with a high electronegativity difference. So for the HF, there's a dipole that's actually a hydrogen bond. And there's also London dispersion, but that's a weaker force in there. So the stronger force in HF is the hydrogen bond. Let's go ahead and try the next one, NaCl. So NaCl is, let's do this color here, NaCl. If we did the electronegativity difference between Na and Cl, you would see that just like as you would predict, because there's a metal and non-metal, that's ionic. You have 3 and 0.9. So when you do, when you do 3.0 minus 0.9, you get 2.1, and that's larger than 1.7, so we have an ionic substance. And so we go to our chart, and the question is, do we have ions? Well, if it's ionic, yes, you do. And the next question is, are there polar molecules present? So what that means is, like, for example, is this salt in water? I would tell you that. I would say this is salt dissolved in water, or whatever be the case. But it's just pure salt. So let's say you just have a tablespoon of salt, just NaCl. So we're just going to say no, it's just NaCl. If it's just NaCl, then it's ionic, and it has ionic bonds holding the ions together. So the Na plus is held together by the chloride by the opposite charges that they have. So when it comes to charges, the opposite charges attract each other. So this is an ionic bond that's holding them together. Not really an intermolecular force, but it's still bonding that happens within the salt crystal. So when it comes to ionic compounds, it kind of acts as both. It's a bit of an intermolecular and intramolecular force at the same time. But we primarily define it as intramolecular. So it is ionic, but just to also let you know, remember, everything does have LDF as well. So everything has LDF, so that means that our NaCl here, the strongest force would be the ionic, even though there's also LDF. Let's try NH3. Notice I didn't use Vesper to draw out the shape of NaCl because it's not a molecule. NaCl, remember, exists as little crystals, a crystal lattice structure, and so it has a crystal shape as opposed to a molecular shape. Okay, so NH3, let's choose that color there. So we are going to do NH3. I will draw out the molecule. That's what I usually do, the Lewis structure. And so I'm doing this fast because we already done a lesson on this. And you can just go back and review the Lewis structures lesson if you're not sure how to do this. And then just to show you, if I want to do Vesper as well, it would be a trigonal pyramid. And so I think it would be something like this. We'd have one going behind, one coming out at us, and then one just in the plane there. And we have to figure out if this is polar or non-polar. So we're going to ask ourselves, one, are there polar bonds? And so if you do the electronegativity difference between N and H, you get, let's go take a look at that. N is 3, H is 2.1. So 3.0 minus 2.1, and we get 0.9, which means that it is polar. So there are polar bonds. And then 2, are there lone pairs around the central atom? Yes. So this is not symmetrical. Therefore, this is a polar molecule. And the partial negative charge would be on the most electronegative atom there, which is nitrogen. And so the overall dipole would be pointing in this direction here with the partial negative up there, partial positive at the bottom. But the point is, this is a polar substance. It's not ionic. It's not an ionic compound. So when we're looking at our chart over here, we're going to be going with the idea that we don't have any ions present. It is a polar substance, so yes. And then are there any HN, HO, or HF? Well, yes, there's NH in there, right? So there is, and that means that we have some hydrogen bonding that's possible there. And so the hydrogen bonding, just to draw it a simplified way, if we're doing this, I'm not drawing the Vesper shape, just drawing a Lewis shape here. This is partial negative. And then if we drew another one here, this is partial positive on the H, and so there would be a hydrogen bond that exists there between them. So for NH3, it's polar. It has a dipole-dipole, but that dipole-dipole is actually a hydrogen bond. And it also has LDF like all the other substances. But the strongest force in here is the H bond. Next, we'll do the CH3OH and the CH3NH2. One more thing to mention as well. The hydrogen bond in NH is weaker than the hydrogen bond in OH. If you do the electronegativity difference, remember OH was 1.4, and then NH was 0.9. So what that means is that the OH one is more polar, and so usually the water hydrogen bonding is going to be more stronger than the nitrogen ammonia hydrogen bonding. So that's something to keep in mind as you go in future lessons when it comes to properties and boiling points and all that as well. So let's see, we were going to do CH3OH. So we're going to draw out the Lewis structure, and you'll get experience doing this, but generally when you have a molecule like this is called an alcohol with the OH here. What you do is you attach your H's to your carbon, not all of them, but most of them, and the OH you leave sort of as is. So you're going to put an O there and then H. And the idea is that I know this is right because my carbon has 4 bonds attached to it, and that's what it should have. It shouldn't have more than that, it shouldn't have less than that, because it follows a complete octet rule. I'll put my lone pairs here. And compare this to CH4. CH4 was totally nonpolar, right? Totally nonpolar. But over here we replace one of these H's with an OH group. So in reality, we have a polarity happening here. We have a dipole happening between the oxygen and the carbon. So if you look at oxygen and carbon, there's a pull there, 3.5 minus 2, so about 1.0. And then also between the oxygen and the hydrogen, so about 1.4. So there's a huge pull happening there, and there's basically a partial negative charge on the O, and then a partial positive charge on the H there. Almost like water, except instead of an H, you have a CH3 group here. But this is how you would draw it. And so just at quick glance, you know this is polar because you added the OH there. And so let me just make my little partial negative there. So because of the OH, it's polar. And because it's polar, you know that you can have dipole-dipole at least. But with an OH group, just at quick glance, you know that you have hydrogen bonding. So based on adding the OH, when you see OH in a molecule, generally, not always, but for the most part, you'll assume that you can see a dipole-dipole, which is actually hydrogen bonding, and also LDF, don't forget. So the strongest force here is hydrogen bonding. And so you could predict, you could say, between these two, which one has a higher boiling point? Well, think about the one that has the strongest forces. This only has LDF. This has LDF as well, probably a little bit more than that one. But the LDF is not what's making the difference here. It's the hydrogen bonding. So because this has LDF and also the strong hydrogen bonds, this would probably have a higher boiling point. I don't know why I put an arrow and then wrote higher, but higher boiling point than CH4, which is only nonpolar and only has LDF. So that's just a quick glance how you can figure that out using the OH group there. Let's go and try the next one. I think it was CH3 NH2. And you can probably bet that it's going to be a very similar way, a similar process here. So CH3 NH2. So if I were to draw that out, same idea, put the 3 H's there, put the N over here, and the H there. And again, that's using your Lewis structure knowledge. Now, again, CH4 was nonpolar because it was only nonpolar bonds. But now we have some polar bonds happening here. We're going to have a partial negative end for a nitrogen and partial positive ends for our hydrogens, for example, and even over here, partial positive. Let's see if it's even a big difference. So if we have C and N 0.5, so it is a little bit polar there. So notice though that just by looking at this at first glance, you know what this is. This is an NH group. So it made our molecule that was methane before that was nonpolar, made it polar. But more specifically, it's now able to hydrogen bond because it has an NH group there. So these are easy because you can look at the NH group or the OH group, and right away you know that, yeah, there is some dipole-dipole that's actually hydrogen bonding because of the NH group. And also there's LDF because everything has LDF. And the strongest force there is the hydrogen bond. So let's go ahead and do the next few. And don't forget, this video is long, but you're going to fast forward as you need to and check your work as you need to. So let's do the BH3 example. BH3. So BH3, let's draw that out as a Lewis structure. And you can also draw it out as a as a Vesper structure as well. But we're just going to deal with the Lewis structure right now. And we're going to see if there's any polar bonds there. Are there any polar bonds? So between B and H, it looks like 2 minus 2.1. That's nonpolar, right? That's nonpolar. So it's a pretty equal share of electrons. So, so 1, polar bonds, no. And then 2, are there lone pairs? Lone pairs around the central atom? No. So that means this is symmetrical, so it's nonpolar. So let's go ahead and take a look at our chart up here. So are there ions? No, it's a molecular compound, it's not ionic. Are there polar molecules? No. So the only real force that we have there is the London dispersion force. So that's the strongest force because it's the only force. And so in this video, we saw examples from H2O to BH3. In the next video, we're going to take a look at the last few examples.